Happy learning! Today we're going to talk about limits. So suppose we want to know the value of a function when x is close to some number c. Okay, you might just be thinking, oh, plug in x equals c and see what the function gives. Well, we're going to see that that doesn't always work. So for example, suppose we have f of x equals x squared minus x minus 6 over x plus 2. And we want to know what happens to our function when x gets close to negative 2. Right? Negative 2 is in our denominator. So it's possible that our function blows up to infinity or negative infinity. But it's also possible that we have like a hole or a jump in our graph. All right, so what happens to f of x at x equals negative 2? That's what we're trying to figure out, right? Negative 2 is not in the domain of our function because we'd be dividing by 0. But negative 1.999 is. So we could figure out what happens when x is close to that. So the first idea we could do is let's take a table of values. And we'll sub in some values for x that are close to negative 2, but a little bit further to the left. So let's say negative 2.1. or negative 2.01, or negative 2.001. All right, and if we were to sub in negative 2.1 into our function, we would get the value negative 5.1. Similarly, if we plugged in negative 2.01 into the function, right, plug it into here, we would get negative 5.01. And here we would get negative 5.001. So it seems like when we sub in values of x that are close to negative 2, but a little bit smaller than negative 2, our function is getting close to negative 5. And now we'll do the same thing, but taking values that are a little bit bigger than negative 2. So maybe negative 1.9, or negative 1.99, or negative 1.999. And when we do that, we get negative 4.9, negative 4.99, and negative 4.999. So when we're plugging in values of x that are a little bit bigger than negative 2, our f of x value is still getting close to 5. Okay, and so we say that f of x approaches 5 as x approaches negative 2. What this looks like graphically is our function gets close to this point, negative 2, negative 5. But since negative 2 isn't in our domain, there's actually a hole in the graph. All right, and so we're calling this a limiting value. So let's define that. Let f of x be a function defined on an open interval containing some number c. All right, so in our case, c was negative 2. It's like the value that we're going to be interested in what our function, how our function behaves at that point. Then we write the limit as x goes to c of f of x equals L. So this is read as the limit of f of x as x approaches c means that as x gets closer to c, f of x gets closer to L. So we could make the value of our function close to L by taking x close to c. Okay, so let's take a look at a few examples. I want us to find f of 2 and the limit as x approaches 2 of f of x. All right, and I'm going to give you 3 examples here. All right, so here's our first one. Our next one is this. And then finally, this. All right, so we want to find, for each of these, f of 2 and the limit as x approaches 2 of f of x. All right, and so in this first one, our function's value is just we go to 2 and we figure out what the function's value is at that point. It's 3. So f of 2 is 3. And to find the limit as x approaches 2, well, what's happening to our function as we get close to 2? The function is still close to 3. All right, so here our function value is 2. Our limit's value is also 2. That's OK. This next one, f of 2, well, there's a hole at x equals 2. So f of 2 is undefined, does not exist. But the limit as x goes to 2 of f of x, what's happening to our function as x gets close to 2? Our function's value is close to -1. So our limiting value is -1. And now finally here, I know this is a little bit small, so I hope you can see that. Our function's value, if we go to 2, our function's value is up here at 3. And the limit as x goes to 2 of f of x equals 1. It's where our hole is. Okay, and so just because the function has a certain value doesn't mean its limit can't have a different value. So here we see a function's value of 3 and a limit value of 1. And so we could kind of generalize this idea of a limit. Instead of having to come from both directions, we could look at one direction at a time. So we write the limit as x approaches c from the right of f of x equals L. This means the values of f of x approach L, as x goes to c, and we're only taking values of x greater than c. All right, so this plus up here means we're coming from the right-hand side. And similarly, we could write the limit as x approaches c from the left of f of x equals L. Means the same thing, so it means the values of f of x approach L as x gets close to c and x is less than c. Okay, and so note, if one of these doesn't exist or they're not the same value, then the limit does not exist. So if the limit as x approaches c from the left of f of x does not equal the limit as x approaches c from the right of f of x, then the limit as x approaches c of our function does not exist. All right, so for example, if we have the following graph, the limit, and let's say this is 3 up here. So the limit as x goes to 2 from the left of f of x equals 0, right? As we travel along from the left, we approach 0. And the limit as x approaches 2 from the right of f of x equals, well, when we come in from the right, our function's value is 3. So this is 3. And 0 is not equal to 3. So we know that the limit as x goes to 2 of f of x does not exist. Okay, another example I want to show you is what happens if the curve goes off to infinity. All right, so another example, let's say we're looking at x equals 1. And maybe our function does something like this. Right, our function blows up to infinity at x equals 1. We would say the limit as x goes to infinity. No, let's try that again. The limit as x goes to 1 of f of x equals infinity. Okay, so it is possible that our limiting value is infinity. Okay, so let me state some properties of limits. So the first is that the limit as x approaches c of some number k. So if our function is just the constant function, well, then our function is always at the value k. So its limiting value is also k. All right, the next property is that the limit as x approaches c of the function x is just c. So it's saying what's happening to our function as x approaches c? Well, our function is the same thing as what we're plugging in, so it's going to go to c. Next, the limit as x approaches c of f of x plus g of x, plus or minus g of x, so this works for both plus and minus, is equal to the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. And this is also true for division. So f of x times or divided by, I kind of am making up this symbol now, times divided by g of x is the product or division or quotient of their limits. Okay, so what do these say? This says if our function is simple enough, we could just plug in the number to get the limit. All right, so I'm going to state that as a theorem. So the theorem says if f of x is a polynomial or rational function and C is in the domain, then the limit as x approaches C of f of x equals f of C. All right, so to evaluate the limit, this is saying the first thing we should do is just plug in the number. If it results in division by 0, that's where the trouble starts. Okay, so for example, evaluate the limit as x goes to 4 of x squared minus 4x over x minus 2. Okay, so we don't have to make a table of values or anything like we did before. We literally could just look at our theorem. We have a rational function, right? The quotient of two polynomials is a rational function. And 4 is in the domain of our function, right? The domain is, as long as we're not dividing by 2, as long as we're not dividing by 0, so x equals 2, we're good to go. And so the theorem says to evaluate the limit as x goes to 4 of x squared minus 4x over x minus 2 is equal to, you just sub in 4 for x. 16 minus 16 over 4 minus 2, which is 0. All right, so it's as simple as that. The first thing you should do to evaluate limits is just plug the number in. Okay, so if when you plug the number in, you get 0 over 0, that's when the interesting things happen. Okay, so if the limit as x approaches C of f of x equals 0, and the limit as x approaches C of g of x equals 0, then the limit as x approaches C of f of x over g of x has what's called 0 over 0 indeterminate form. Okay, in this case, so if you get 0 over 0, we should try factoring. All right, so when you plug, this is saying when you try to plug in the value, if you get 0 over 0, factor, cancel, try again. All right, let's take a look at an example. So let's evaluate the limit as x goes to 1 of x squared minus 3x plus 2 over x squared minus 1. All right, so the first thing we should do is just plug in the value into our expression. If we don't get 0 over 0, we're done. Okay, so plug in the value. If we don't get 0 over 0, you're done with the problem. Move on to the next one. Well, what happens, we do the limit as x goes to 1 of x squared minus 3x plus 2 over x squared minus 1. We plug in 1 for x. We get 1 minus 3 plus 2, 0. Uh-oh. 1 squared is 1 minus 1 is 0 over 0. We are in indeterminate form. When you get 0 over 0, buckle up because there's more work to do. All right? It means there's more work to be done. Okay, so 0 over 0 just means keep going. Let's factor. X squared minus 3x plus 2 over x squared minus 1. The numerator we could factor. And the denominator we could also factor, right? It's the difference of squares, so that factors easily. All right, and you could see there's an x minus 1 in the numerator and denominator. Those simplify to 1. All right, and so now we could evaluate the limit as x goes to 1 of x minus 2 over x plus 1. Again, let's plug in the number and see what we get. When we plug in 1, we get negative 1 over 2. All right, so the value of this limit is negative 1/2. Okay, I want to do one more example looking at limits of piecewise functions. Because with piecewise functions, how do you just plug the number in? It's a little bit trickier. All right, so let's take a look at a piecewise defined function. So let's evaluate the limit as x goes to 1 of f of x. And then here f of x is a piecewise defined function that's x squared plus 1 if x is less than or equal to 1, and it's x plus 2 if x is greater than 1. Okay, so to evaluate this limit, when you have a piecewise function, we need to evaluate a left-hand limit and a right-hand limit and see if those are the same values. Okay, so let's evaluate the limit as x goes to 1 from the left of f of x. So remember, when we're evaluating the limit from the left, that means we're subbing in values of x that are slightly smaller than 1. We're going to be using this rule. All right, so that's the limit as x goes to 1 from the left of x squared plus 1. And we could evaluate this by just plugging the number in. Right? There's no denominators to worry about. So we just plug in 1 and we get 1 squared plus 1, which is 2. All right, so the limit from the left of our function is 2. Now let's evaluate the limit as x goes to 1 from the right. All right, so to evaluate the limit as x goes to 1 from the right, we're subbing in, you can imagine we're subbing in values of x that are slightly bigger than 1. Which rule do we use when our x value is slightly bigger than 1? We use this rule, right? X plus 2 if x is bigger than 1. So slightly bigger is bigger. So it's the limit as x goes to 1 from the right of x plus 2. And again, how do we evaluate this? We just plug in 1. 1 plus 2. You literally learned how to do that in kindergarten. 1 plus 2. And we get a value of 3. Our left-hand limit is 2. Our right-hand limit is 3. These are not the same value, right? 2 does not equal 3. Therefore, the limit as x goes to 1 of our function does not exist. If these two values were the same, then that number would be our limiting value. But since they're different, the limit does not exist. What this looks like graphically, x squared plus 1 is a parabola, and x plus 2 is a line. This is what the graph looks. This is what our function looks like graphically. And so you could see, as we approach x equals 1, we got a big jump. There's a big old jump in the graph. And so that means the limit does not exist. You may not have known this, but this was our first lesson in calculus. Okay, so limits kind of make up the math behind calculus, and that's what we're going to be looking at for the next few lectures. So let me know in the comments if you have any thoughts or concerns about limits, but I'll see you next time. Bye-bye.